Okay, we are now up to problem 14, and now we're starting the section of the class that talks about exponential functions and logarithmic functions. In fact, this may be just about the last part of the class. I went ahead and copied down, actually, this is problem 14, but in a minute I want to do a second kind of problem so you can see the difference. I went ahead and wrote down the table to save time. The problem 14 says, determine whether the function given by the table is linear, exponential, or neither. If the function is linear, find a linear function that models the data. If it is exponential, find an exponential function that models the data. When they say models the data, that's a fancy way of saying find the equation. And if it's linear, a linear equation, typically we use y equals mx plus b, where m is the slope and b is the y-intercept. So what I'm going to do is I go check to see if this data indicates a linear equation, and if it does, then I try and find the equation. But then if I look at the data and it says it's an exponential equation, the exponential equation is written like this. So, how do you go about checking to see? Let's first check to see if it's a linear equation. The way you check for a linear equation is, you notice this first column are values of x, and the second column are the f of x, or we can also think of it as y. What I'm going to do is calculate this little triangle indicates the change. In other words, how much does y change? I'm going to look at how much, so I'm looking at the first two sort of points here. How much does y change divided by how much did x change? In other words, x goes from -1 to 0, and therefore y goes from 2 to 8. So the change in y, you always start with the final value. So how did y change? It ended up at 8. It started out at 2. So the change was 6. All right, that makes sense. If I ask how much did y change? Went from 2 to 8. It changed 6, which is 8 minus 2. Divided by how much did x change? X began at -1 and went to 0. We do the same thing. You take your final x point and you always subtract the previous. So 0 minus a -1. So when you do this math, you end up with 6 over 1. And this, actually in the book, if you look at the example, they call this the average rate of change. I'm not going to write that here. I don't have enough room. And I do this calculation for every 2 points. Now I'm going to go from the second point to the third point. So I say, how much did the y change? 14 minus 8. So this one goes with this one. This one, how much did my y change? It went from 8 to 14, so it changed by 6. How did the x change? It went from 0 to 1. It grew by 1. Therefore, the average rate of change is 6. The next 2 points, from 14 to 20, it grew 6. From 1 to 2, it grew 1. And the last two, from 20 to 26, it grew 6. From 2 to 3, it grew 1. Now, if all these numbers here are the same number, then you have what's called a linear model, or basically you can say we can write an equation with this slope-intercept form. This is the equation for a linear model. So I can stop right now and I can say, basically I can now write a linear equation that describes how these x's and y's are working. As a matter of fact, what you do is, here's our equation that we use. So it turns out this number here, I calculated 6666, that ends up being the m. Do you remember a long time ago when you learned what the slope is? You learned this equation, y2 minus y1 over x2 minus x1. In other words, how much does y change over how much does x change? That's what we did right here. How much did y change over how much did x change? So I know already m is 6. Now if I can figure out what b is equal to, b is called the y-intercept, then I am done. Easiest way to figure out b is, I just take one of these sort of points, the x and the y value, and if I plug them in here, I can find the b. Matter of fact, to make it really simple, I'm going to choose the second point, because actually the second point's called the y-intercept, but I'll go ahead and plug it in just to show you. So I'm going to plug in 0 for x and 8 for y. So y is 8, x is 0, and when I do that, I realize that b is 8, so therefore this is the equation for this data. In other words, for each row here, if you plug in the value for x into this equation, you'll get the y. If I plug in minus 1 for x here, what's y equal to? 2. If I plug in 0 for x, y is 8. If I plug in 1 for x, it's 14. So now this equation, we say, describes or models this data. And that's actually what scientists and people in research do. They try and take data and they see if they can come up with some equation that models or describes the data. So the actual 14, the problem was a linear model. This is the equation. Just to show you the difference now, from the book, I grabbed another table of data. Say you were given this, the first step is still to check to see if you have a linear model. So I'm still going to calculate change in y over change in x. So here, I end up at 16. I start with 32. You always take the final value minus the initial value, and 0 minus a negative 1. This is negative 16 over, this ends up being negative 16. For the next one, 8 minus 16 over 1 minus 0, just 1. This is negative 8. For the next 2 points, 4 minus 8 over 1, negative 4. For the next 2 points, 2 minus 4 over 1. First thing I notice is it's not linear, because for it to be linear, these numbers would all be the same. Remember up here? These numbers are all the same. Then I was to stop and say, hey, I've got a linear model. These are not the same. It's not linear. The next thing you do is you go and check to see if it's an exponential model. And the way you check for an exponential model is you simply look at the y's here and you take the ratio or fraction of how your y's change. By that I mean you take your final y divided by the initial y. Now if I compare these 2 points, I take the final y divided by the initial y. These 2 points, the final, or I call it the second y, divided by the first y. And the last 2, the final divided by the initial. Now if you do this little test, and these numbers are all the same, that means we have an exponential equation. And as it turns out, this number right here, here's the equation. What we need to find a number for C, a number for A. Turns out this number here ends up being the A. So far, here's my equation. Now if I can figure out the C, I've got my exponential equation. Easiest way to do that is, once again, to go over here and pick an x and a y. And I'm going to once again pick x is 0, y is 16. So if I plug that in here, I plugged in 0 for x, 16 for y. Now what is 1/2 to the 0 power? Anything raised to the 0 power is just 1. So this ends up being c equals 16. So now that I know c, I can say my exponential equation is 16 times 1/2 to the x. All right, so these kinds of problems are not necessarily hard once you understand what to do and remember how to do it. Tricky part is remembering what the procedure is. The procedure itself is not hard as long as you can remember it. All right, so moving on. Let's look at problem 15. Now 15 is another graph. And here's how I do these graphs. I try and use common sense, and I try and use I'm going to try and make this larger so we can see it. Because what we have here, they say match the graph to one of the following equations. See if I can focus this. Make it a little lighter. So here's an equation. This is actually an exponential equation. And they give us, looks like, 8 different exponential equations. And they're saying, which one of these equations does this graph match? Here's what I do. I just try and use process of elimination. What do I mean by that? This graph, this is the x-axis, this is the y-axis. I'm going to pick a point on here. For instance, I'm going to pick the origin. It looks like one of the points on the graph is 0, 0. When x is 0, y is 0. So I'm going to go to each of my equations and actually plug in 0 for x, and I'm going to see if y equals 0. If it does, then that potentially could be the equation. And I think when we do this, you're going to see that a lot of these equations automatically are eliminated. For instance, this equation for A. What happens when I plug in 0 for x? Let me try and write how I get y equals 6 to the 0. Well, what is 6 to the 0? 6 to the 0 is 1. So I end up with y equals 1. but that point is not on my graph. My graph is 0, 0. So I plugged in x equals 0. I did not get 0 for y, so therefore I know it's not A. How about C? What happens when I plug in 0 for x here? 6 to the 0 is 1. You got a minus out front. In this case, y would be negative 1. Well, that's not correct either because y is supposed to be 0. How about this next one? When I plug in 0 for x, 6 to the 0 is 1. 1 minus 1 equals 0. This, I don't know for sure yet, but it could be the graph. At least this one point works for this equation. I don't know for sure yet because there might be another possibility. Let me check the rest of the equations. So let me keep going and let me keep plugging in 0 for x. When I plug in 0 for x here, 1 minus 0 is 1, you get 6 to the first. This equals 6. Y does not equal 6. Y is supposed to be 0. How about this one up here? When you plug in 0 for x, you get 6 to the 0, which is 1. That's not correct. How about negative 6 to the negative x? You plug in 0 for x, you got 6 to the 0, which is 1. This whole thing equals negative 1. It's not that equation. If I plug in 0 for x here, 0 minus 1 is negative 1. This is 6 to the negative 1. Actually, ends up being 1/6. Y is 1/6, definitely not 0. So far, I've only found one equation that the point 0, 0 actually works. Let's check this last one. If I plug in 0 for here, 6 to the 0 is 1. 1 minus 1, this one equals 0. So, for the point 0, 0, only two of the equations actually work. So now I've narrowed it down to the equation has to be either E or H. Now I need to figure out which one it is. Now for this one, what I do is you can do a couple things. How about I look, my actual graph, you notice as x gets larger and x is positive, like when x gets to be 1 and 2, the value of y is positive and gets to be large very quickly. So let's see what happens. Let's go to each of these two possible equations and see what happens when I plug in a large number for x. Just basically what's the trend. So for E, if I plug in a large number for x, say 10, I would have 6 to the 10th minus 1. 6 to the 10th is a huge number, and it's a positive number. So I'm saying, yeah, I could see that looks like that's a possibility. Let's go see what happens with the equation for H. If I plug in 10 for x, so this one is E, this one is H. When I plug in 10 for x, I get 1 minus 6 to the 10th. Now 6 to the 10th is a huge number, but look what happens. 1 minus it. So this y becomes a huge negative number. That's not what happens here. When my x is out here, when it's a positive number, I get a huge positive number. That means, as it turns out, it cannot be H, and it has to be E. So that's just, it's called the process of elimination. You just try, like, first of all, I picked a very easy and common point. Normally, I always pick when x is 0, what is y? And I go and look at all my equations, and usually you can eliminate equations pretty quickly. In this case, I narrowed it down to two possibilities, and then I did one more sort of check and was able to determine the correct answer. All right, so actually that kind of problem, really not that difficult. Here's another kind of sort of graphing kind of problem. Let me just show it to you here. Begin with the graph of y equals e to the x. Use transformations to graph the function, then determine its domain, range, and horizontal asymptote. So basically, we're trying to figure out information about this equation, f of x equals e to the x plus 7. And here they're sort of telling you how to do it. Now honestly, between you and me, when you take this test, if this problem's on the test, you're going to answer the questions, and when you hit the button, it's going to check your answers. Now that computer doesn't know how you came up with those answers. It's just going to check your answers. In other words, here they're saying use transformations to graph the function. And that certainly is one way to do this problem, but there could be other ways. Now, as it turns out, I'm going to go ahead and use transformations, but some of you, I know transformations can be a lot to memorize. That's where those shifts, left and right, up and down, flips and stuff. Sometimes, you know, what you can do is, if you're on a test and you're not sure, you can't remember all the transformations, you can always just do the old-fashioned data table where you pick a few numbers for x and figure out the y, and then try and draw your graph. Now I'm going to go ahead, if I plot, or try and make a plot of e to the x, it looks something like this. I know one thing, it goes through, when x is 0, y is 1. And then it looks something like this. And this actually probably goes up even faster than I've shown. But the idea is, it goes through this point here. As x gets to be more negative, the graph gets very close but never ever touches the x-axis. The x-axis in this case is called an asymptote. An asymptote is the line that the graph gets close to but never touches. So this is the graph of y equals e to the x. Now, because I actually have done this a while, this is a pretty easy problem to do with, in this case, a shift, because whenever you add a number to the x, what it does, it causes this initial graph to move 7 to the left. So in other words, this point, instead of being at 0, 1, it's going to be at negative 7, 1. And this whole thing just shifts over 7. So basically it would be, of course my picture's not perfect, but the difference here should be 7, because the whole graph is just moved that way. But you notice here what happens, my new graph, it still never touches the x-axis, even though my picture's not great. So this right here would be the graph of e to the x plus 7. All right. Now if you can't remember this or have a hard time, if you just plug in data points, if you got your calculator and you plug in 3 or 4 points, you can still sort of plot this, and then you're still able to answer the rest of the questions. For instance, the domain are the possible values of x. So what's the smallest value of x for this equation? Well, this thing goes on forever and ever. So the smallest value of x is negative infinity. How far does it go to the right? What's the largest value of x? Even though this thing goes up, as it's going up, it's still moving to the right. So theoretically, it also goes to infinity. The range is the up and down, the possible values of y. So we say, what's the smallest value of y? Well, in this case, this graph never crosses the x-axis, but gets very, very close. So what's the smallest value for y? What we do is you put a parenthesis and a 0. Because it never quite gets to 0, but gets very, very close. So we say the range, the values of y go from 0, and what's the largest value of y? Infinity. So here they actually ask you, what is the horizontal asymptote of this equation? And like I've been saying, in this case, the asymptote is the line that my graph gets close to but never touches. And in this case, it's the x-axis. If you write that as an equation, it's y equals 0, because that's the value of y at the x-axis. All right, so that also isn't too bad, although it can be a little tricky finding the graph, but once you get the graph correct, the answers are pretty easy. All right, let me stop now, and we'll pick up the next video with problem 17.